Okay, troops, I'm going to see if I can just do a redo here. So remember we talked about if I have some water and if I put some object into the water, oh, this thing's all jumpy for some reason. Probably time to reboot the computer, as my son would say. But anyways, remember we talked about in principle well, not in principle, for sure, if we were very careful, we could measure what the delta volume here is, and then we could, whatchamacallit, we would know the volume of the object. But we're not going to do it that way because we don't have very well marked off beakers, for example. But we are going to use this concept of displacement. And what happens is, first of all, a lot of people used to believe, I think, or we're told, I don't know how long it took, but at least in Archimedes' days, they sort of felt like when you got into the water, the water sort of went into you and you sort of like became part of the water. But Archimedes, the famous scene of him running naked and screaming Eureka happened when he climbed in the bathtub that was too full and it overflowed, and he realized, no way. And in fact, his great leap was that when you put this object in here, the volume, in fact, you can just think of this. This is the volume of like just water. And then if I put this object in here, then this is the V, there's going to be some V total here now that's going to equal the V water and the object. And that's why we can think of the delta V is caused by the object. So we say that it replaces, and when you displacement, we say that the object comes in, it pushes the water away, and it replaces it in some way, you could say. So we say it displaces it, because that combines the concept of pushing it out of the way and replacing it. So, if we could weigh that same volume of water, the delta V, which is the same volume of water, which of course is also the volume of the object, and the delta volume, I suppose you would call it here, that change in volume is the volume of the object. And if we were to weigh it, that would equal the force that's pushing the object up. Excuse me. And the model is that the water is pushing, I forget exactly, water pushing from all sides, but there is always a net force of buoyancy. It's too bad. I'll have to find and check on that, because you may need that for depending on where you go in your lecture class. So if we know the density of the water, H2O, in grams per centimeter cubed, we can see where, so it may not be convenient to actually weigh that water because, for example, once you put the object in there, we can't just weigh the speaker, this combination, that won't work very well. So we could imagine maybe like filling it to the very brim and then collecting the water that overflows. Or we can just say, look, we can take that volume, which is in centimeters cubed, and we can multiply it by the rho. That's grams per centimeter cubed, the density, and look at that, we can get a mass. And we simply have to multiply it by the force of gravity to get a weight or a force, but that adds the weight of the water, the mass of the H2O displaced, multiply it by G, you get weight, and then we use our postulate here, or maybe it's hypothesis because it can be proven, it can be measured and tested. So at the end of the day, then, we can simply say that same thing. Here's the rho of the water. It just happens to be in kgs per meter cubed. I guess I could have put it in centimeters. I think I did change these. So that's one important idea for the beginning, the background. So that's equation 1. So then if we take a look at equation 2, what does equation 2 tell us? So equation 2 says, now this is pretty straightforward, because we know by definition the density of some object is always, we just weigh it, and then we divide by the volume of the piece we just weighed, and then we know, not only do we know the rho of the object, we know basically the rho of the object's material, really, if you think about it. It's not the object itself. Because objects, you can't just say this object has this density or that density. You say this material has this density and that density. You say an object has a mass and it has a volume. So once again, just as we did before, now if we have a certain volume of an object, we measure it, we multiply these two numbers together, that gets us the mass of the object. But it also, then we can get the weight of the object. Now, the key here that lets us do to get equation 3 is that in the situation we've created, the particular situation we've created, we can substitute into here V water. And let's see, I didn't prepare enough. So then, let's make this little again. I should pause the recording if I can find the... Here it is. I can't believe I've had this thing pause and I don't even know where I left off. Oh, I'm pissed. Okay. Pretty sure I got this part. We figured out that the buoyant force is, we assert that the weight of the displaced water is the buoyant force. So if that's true, then this equation will let us calculate the buoyant force. So then the next step is, this is an equation here that's always going to be true. We don't normally bother with this. We just say weight equals mg. But if we know the density of an object and we measure its volume, we can multiply the two things times the acceleration of gravity, and we can calculate the weight of an object without actually using a scale. Okay. And then what we do to make equation 3 out of equation 2 and 1 is that we're going to say, look, we determined that when we drop this thing into water, the volume of the object is going to equal the volume of the water displaced, which is the delta V. And then we can say, okay, if that's true, we can divide these equation 2 by equation 1. Most of this cancels, and we're left with, yeah, something's funky about the tablet, so it's making my handwriting even worse than ever. But I'm left with this Archimedes equation here, Archimedes principle. Now, we are going to weigh the brass separately and calculate a force, a weight, when we're going to determine its mass. Archimedes didn't have actually such an had accurate scales, but he just had to prove that the density of the crown was less than the density of gold. So, I mean, he didn't even have to say brass and gold. He just had to know that if he would know that, good question. Maybe you do need to weigh it somehow, but we'll table that for the time being. We did a little discussion of this in class. And this is the same stuff. I'm going to pause once more, and hopefully I won't forget to unpause. All right, now just to make sure I set it, we're going to calculate the density of the brass by using what I said, as I said before. Archimedes just said we're going to call the row of water 1. We have a weight of the brass, and we can divide by the buoyant force on the brass, and we can then see what the row of the brass is. Now, another thing we're going to do, though, is because we don't feel like we have a good way of measuring volume, we're going to determine the F buoyancy in a different way. So what we know is that we have some object, and it has a weight. And you could say there's a normal force, but let's just, well, what normal? How is there a normal force here? Because we're hanging it by a string, so it has some tension. Okay, so let's say we have some normal. Then we submerge it in a fluid, and now we have some F buoyant. And of course some other N. This is N submerged. It's not the same. But what we care about is that we also know that in here we have a weight equals to mg. Here we have hold on and pause. Yeah, I'm pretty toasted out. It's already almost 7 o'clock. Okay, so now when it's submerged, so the tension is also the reading of the balance. And that's why they say, like, mass apparent. This is the actual weight, the actual mass. And now that we have this buoyancy force here at the same time, this is a different T. So this is, say, let's just call it apparent, I suppose, and this is real. So we have to be a little careful. The thing that we read out is this tension, if you will. That's what the scale tells us. So that means then that in this case, the T, well, let's hold off for a minute. So now we can see that weight that this thing sees is going to be smaller by this amount here. And you can just use the free body diagram idea, because you say T apparent plus the weight plus FB has to equal 0, and these being vectors. So if we call W, if we do plus down, so that means it becomes minus T plus W minus FB, and they see that equals 0. So I just bring the T over, and I get this equation. So what do we see then? Gravity is gravity. So this has to be mass, the actual mass. So does that. But we can now say, okay, why don't we just say, instead of that, we'll say mass apparent times G. You know, strictly speaking, this thing measures in grams, not newtons. And then F buoyancy, give me a minute. Well, we'll just keep it F buoyancy. So we can just divide everybody by G, and we get mass apparent equals dmg minus F of buoyancy over G. And we have mass real equals to the weight divided by G. And let's just see what we got here. What do we actually want? This is real, and it's no G. Pause time. Okay, so we did it with forces, and just keep in mind that the T is going to be the mass from the balance times G. In general. So in this case, we're going to be measuring the actual mass. So that means that we have now the weight equals to the mass actual times G. And here we have, again, because they have to be summed to 0, and we can then put in the signs, we see that we have T minus equals W minus F of B. Yeah, so how would we get this? This is going to be the apparent so if we were to take the mass real times the acceleration of gravity and subtracted, no, we don't want to do that. We want to take the mass apparent times gravity here and subtract W mass actual times G, we end up with the buoyancy force. Let's make absolutely certain. Whew, yeah. If we now say mass apparent, that's mass apparent times G. And if we subtract W, we're actually, are we going to end up with minus force of B? Yeah, it doesn't really matter. It's just we chose down to be the positive direction. Maybe we should have chosen it as the up direction. So mass apparent minus mass actual will get us F of B. Okay, got it. Okay, so let's take a look here. So we got a bunch of things we're asked to measure. So we got to measure the mass, the brass block, volume, and then we have a formula. and measure the apparent, okay, this is measure the apparent mass by having it in water. So first you measure dry, then you measure it hanging in water. And so does the dimensional volume of the brass agree with the Archimedes volume? Oh, that's way too difficult. Well, and we already did it a different way. No wonder they have that page 2 of those handwritten notes the way they have them. I don't see the point. It's not as intuitive, I don't think. Use the math with whichever volume measurement you have. Come to trust more to determine the density of the brass. So, what? That is not the tail chasing the dog. Okay, so part E is just stupid. No wonder we couldn't figure it out. Combine the already estimated in the, yeah, okay, so that's where we go to the spreadsheet. And so let's pull that up. So we have the mass of the brass and the balance are plus minus. Then we have the capital D, the little d. We calculated d squared, big D squared minus little d squared because we needed to calculate an uncertainty on that quantity. And we did a little thought experiment in class, and we were going to decide to blow it off, but we said, it's not that much different. So then I have my L plus minus L. All right, so the first big hurdle was the volume's okay. It's pi over 4, and let's see, let me zoom in for you. So the volume, as advertised, pi over 4, something squared minus something else squared. Now you see them. Capital D squared minus little d squared. And times the length. So now we need an uncertainty. So in this case, we already did the uncertainty of the two things that are subtracted from each other. And let's take a look at it. And in this case, notice it's J6 and L6 are only the plus minuses of capital D and little d. They're not being divided. So these are absolute errors, not relative errors. So that means that when you add and subtract numbers together, your errors are going to grow more than if you were multiplying and dividing, which is kind of ironic. And it gets really bad. Notice this is going to stay the same because no matter what the final value is. And let's see here we didn't actually multiply by that thing's value. See, it doesn't scale with the value of the quantity. And so what happens then, if you subtract two numbers that are close together, you can ironically end up with something that's smaller than the uncertainty. And that's a pain in the ass. Something that a lot of times when you do an experiment on one detector, especially in my field, and then you want to compare it to an experiment on another detector, and you try to assign error bars, it can become a nightmare. And that's one of the reasons why the particle detector I worked on for my PhD was able to accelerate both protons and gold nuclei at different times. But what was nice about that is that it allowed us to be able to compare numbers from protons and gold nuclei directly, and we could just do divisions instead of subtractions. Really key. Okay. So there's our. So now what we're going to do for our error propagation of volume, we're going to say that the plus minus vol is going to equal the volume times plus minus, and I'm going to use that symbol for d squared minus little d squared divided by its value, and that's got to be squared, and plus, because it's times, then it becomes plus minus L over L squared, and then we take the square root. So this should be very familiar. And so we'll scroll over here. Let's see if we can keep the relevant things on screen. I think so. So there it is. Well, you can always pause this, so I don't have to wait. And then at the end of the day, and we don't need the dollar signs, but density is mass divided by the volume. So we have this in grams per centimeter cubed. And then we do similar thing as we did up here, but now it's the plus minus mass over the mass squared, and then plus minus the volume over the volume. And then the plus minus, so this will be the value of rho here, because we wanted the plus minus of the density, and that's what would go here, and that's S6, see? And it turns out that the accepted value is 8.40. So that's not bad. Now, what also we wanted to do is calculate the rho of the brass using Archimedes' principle. And that's pretty interesting that they came out. I'm going to add a decimal place here. Let's see if there's any difference. I'd be a little suspicious if they're both exactly the same, because that just meant, I don't like that they're both exactly the same. Too bad. Because we got this density by taking physical measurements, right? Now we want to take the density, and the plus minus on the density is actually going to be dominated by the plus minus of the mass measurement, I think. Let's see, plus minus volume is 0.064. That should be pretty small because of the calipers. Plus minus is 0.01. And look at that. The plus minus is smaller. But the relative error is much smaller because 0.01 over 363. Okay. So it's still dominated, but it should be dominated by that guy. See, I'm not so sure. I would have expected the mass to dominate. Okay, because we use calipers, they're so accurate. We'll just have to see. Maybe this could be done better, but that's all right. We don't care right now. You can't really be wrong. You just explain to people what you did. Okay, so Archimedes' principle requires weight of the brass and well, it doesn't have to be in newtons, but I just decided to do that. So I have it in grams, so I have to divide by 1,000. Then I multiply by 9.8 meters per second squared, and I get the in newtons, and then plus minus is pretty simple, because since I'm multiplying excuse me, let me put this back. I'm multiplying divided by numbers that have no errors, then it's the square root of only one thing squared, so I don't even need the square root symbol. So this is H6, which is the mass, I think. Let's see, what's H6? Right, so that's the plus minus mass over the mass, and I just had to multiply it by the value of the newtons to scale it, which is nice because that takes care of what do I do about the 1,000 and the 9.8 as far as scaling the error. But as long as I use the actual value, it's already scaling it for me right there. It's folded in. And you can see, since it's only dependent on the plus minus of the mass, you can see where, see, this is a 3.56. and the mass is 363. So they're off by about a factor of 100. So if I divide 0.01 by 100, we get this. It's the same thing. So I'm pretty confident this is a good number. One nice thing is that rho of water is good for grams per centimeter cubed or kilograms per meter cubed. Got to put this here. This is the plus minus F buoyancy. And I just call it a buoy. And so FB, what did I use FB? I used W6, density of water, times Q6, which I think is the volume of displacement. Yeah. Well, it's actually, so that is actually the measured volume, right? Because that's what we know. All right, I can kind of see different ways, but we're going to use that measured volume. And since we want to put it into newtons just to be safe, I multiply by 9.8 and of course divide by 1,000. And so that's pretty interesting how we came to that, because you would have expected it was going to be complicated, because it's the let's go back and show it's the volume times the rho of the water, right? So you would have expected that rho of the water is we have it in grams per centimeter cubed. Well, that's safe. But I want everything in meters cubed and kilograms, so maybe I have to, what is centimeters divided by 1,000 cubed? But let's be careful. So we got the density, we multiply it by the volume, which is centimeters cubed. That's all right. And then we're going to multiply it by 9.8 meters per second squared. So we see how we are, if we don't do anything, we get grams, meters per second squared, but we need kilograms. So all we have to do is divide that by 1,000. And that will get us our F buoyancy. And in this case now, what's our plus minus? Well, in this case, since the only thing in this equation that has a plus minus is the volume measurement, that's all we need. We don't, and I just eliminated the square root, because you take the square root of the square and that's it. You don't have to square it. And also, once again, the factor of 1,000 is taken care of because I'm multiplying by the value of F buoy. So remind you that now this is plus minus FB is going to be FB times the plus minus volume over the volume. And the factor of 1,000 is already built into the FB, so we're all good. Okay, so now we can calculate the density using Archimedes. And so we have U6, which is the weight of the brass, times W6, which is the density of the water, and divided by X6, which is the force of buoyancy. And we can come up with a plus minus, which is important. So now we have the force of buoyancy, which is the y and x here. So we have to do that plus minus FB divided by FB times square it, plus the plus minus volume, is it? No, the weight of the brass. The weight, that's where it is, divided by the plus minus of the weight divided by the weight, squared, square root it, times the actual value to scale it. So now, which is too bad because the actual value being 8.4 450. If I subtract the 0.012 here, wait a minute, maybe I'm wrong. Oh crap, maybe we did get, oh gosh, see, I was so tired in class earlier. 8.454.012. 2 and 4 and 4. No, we didn't make it because it's 8.450. Oh no, we did. What am I talking about? The difference between them is only 0.0. I might have made a mistake here, but double check. But it looks like the plus minus is big enough to cover it, and double check. I feel stupid now because in class and in the Zoom recording, this is what we came up with. Okay, maybe I am going to. It's already 35 minutes here. So we've done the bit about Archimedes' principle. For sure, we're within plus minus 10%. We're within plus minus 1%, and I would say we did a pretty good job. Let's just go back here. I somehow think where's the accepted value here? 8.40. Ah, there we go. 8.40. So then, right, the spread doesn't cover. Okay, so right. But even so, if I say to myself, look, 8.40, 10% is 0.8, so we're within plus or minus 0.8, and what is the actual difference is 0.05. Yes, you see that's bigger. It's 0.05, and if you will, 4, and we divide 8.45 into that, you can see that it's less than 1%, I believe. It's about 1%. So to me, I think that's pretty damn good. You can think of just doing a basic percent difference if you like. I'm just looking at a fractional difference here, and it's not very much. So I think that's pretty darn good, guys. So that's we did now the background. We did now the whether or not we verified it. Part 2. Okay, I'm going to pause a moment. In fact, I'll stop this because it's almost 40 minutes.